When we're studying chemical or physical change for that matter, one of the most important things we can do is to keep track of the energy. And one of the sort of overarching principles here is that ultimately nature is lazy and it always wants to go to the lowest energy possible. How do we know this, or why, what's a good example of this? Well, water flows downhill, right? Water flows to its lowest point. And natural processes tend to occur in the direction that leads to a lower total energy of the system. Now we can play some games with that in different specialized systems, but for the most part, this is really where we are. And this all kind of leads back to one of the laws of thermodynamics. Energy cannot be created or destroyed. We can change its form, but we can't create or destroy it. So the two types of energy we most commonly deal with are potential energy, and that's energy of position or stored energy, like the water on the top of a hill or a compressed spring, or chemical bonds are a way of storing energy. And then we have kinetic energy. Kinetic energy is the energy of motion. So when the water is moving, or the molecules are moving, or heat is moving, that's essentially a way of measuring kinetic energy. When we're looking at units, we've got a couple units to work with here. The common unit for energy is the calorie. And we'll get into this in a moment, but be very specific. Notice that I'm talking calories with a little c, abbreviated CAL. And a calorie is the amount of energy needed to heat 1 gram of water by 1 degree Celsius. So lots of ones makes some of those relationships a little bit easier. When we're talking in a more scientific context, the unit we'll most often use for energy is the joule or the kilojoule. And a joule is 4.184 calories, or 4.184 joules is 1 calorie of energy. And again, both joules and calories for that matter are really, really tiny energy units. So often we're going to be using kilocalories or kilojoules. One thing to be extremely careful about is that dietary calories are not the same as the calories we're talking about here. Dietary calories, because calories are so small, dietary calories are actually thousands of non-dietary calories. So dietary calories should usually be with a big C calorie. Regular calories, small c calories. So just to make the terminology a little bit more complex, calories and calories are not the same thing. So use the context of the problem, the context of your situation, to try to keep straight which of those you're really talking about. Now, when we think about energy, we talk about kinetic energy, potential energy, but we can also think about just some of the forms that those take. And one of those forms is heat. Heat is when we transfer energy due to a difference in temperature. And this is one of the things that we often, just in our regular vernacular speech, we talk about formally incorrectly. Especially at this time of year when we're starting, at least in Moorhead, to get on the cold side of things, we often talk about the cold seeping into things, and oh, I've really felt the cold. Well, if we want to be really, really picky about it, you don't feel cold, you feel an absence of heat, because cold isn't a thing. Cold is just the absence of heat. When we're talking about something moving, when we're talking about energy transfer, what we're talking about is formally heat. So how do we measure that heat? We measure heat using temperature. We're going to use a few different temperature units. The one that most of us in the United States are most familiar with is Fahrenheit. In the Fahrenheit temperature system, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. That's a range of 180 degrees Fahrenheit. 32 and 212 seem like kind of picked out of nowhere numbers. They make a little bit more sense when we think about 180. Mathematically, 180 is a number that comes up pretty often. And an important distinction here, Fahrenheit is an arbitrary temperature unit. And when I say arbitrary here, I mean that at some point, somebody just decided, hey, let's call the freezing point of water 32 degrees. Let's call the range 180 degrees to get us up to 212. So it was arbitrarily chosen, and it doesn't necessarily relate specifically to any particular energy scale. It's just a way for us to scale energy. The other common energy unit that we'll come across is Celsius degrees. And here water freezes at 0 and boils at 100. So this is more metric, more SI in its feel, because that range is 100. We've got water boiling at 0. Water freezing at 0, water boiling. But again, this is an arbitrary unit, because the only reason we call this 0 is because someone decided that water was especially important. So we picked water as the substance which defines our temperature range. So it's an arbitrary unit. To avoid some of that arbitrariness in our temperature unit, we're also going to be using a temperature scale known as the Kelvin scale. Kelvin is an absolute unit. So as opposed to these arbitrary units, Kelvin, an absolute unit, at 0 Kelvin, there is 0 energy. So all motion stops at 0 Kelvin. And relating that back up to our more common temperature scales, where does water freeze? Well, water just happens to freeze at 273.15 Kelvin. Boils at 373.15 Kelvin. The range here is 100 Kelvin. So the size of each Kelvin unit is exactly the same size as each degree Celsius. The difference being one of them is an arbitrary unit, one of them is an absolute unit. What about doing conversions? Temperature conversions ultimately aren't that hard, but they're not our typical conversions. We can't just pull a fraction out and do a multiplication and be done. We have to put it in a little bit more context. So if we want to convert between two temperature units, and any two temperature units, it really doesn't matter, we need to have some point where we know that these are all expressing the same amount of energy, and we need to know the size of the unit that we're working with. So whether we're talking about Fahrenheit, Celsius, or Kelvin, we need some reference point, and we need to know the relative size of those units. So let's look at a conversion. Convert 49.38 degrees Fahrenheit to both Celsius and Kelvin. So first, let's do Celsius. Pick a reference point. Why not use the freezing point of water as a reference point? So the given temperature, 49.38 Fahrenheit, is 49.38 minus 32. It's 17.38 degrees Fahrenheit above the freezing point of water. Okay, so now we've got a reference and we've got a size of that energy change. Now we're going to use the relative unit size to convert from Fahrenheit to Celsius. So 17.38 Fahrenheit for every 180 Fahrenheit degrees, right? That's the same size as 100 Celsius degrees. So we put that together. Make sure you use your units so that they cancel correctly. That tells us that our temperature is 9.656 degrees Celsius above the freezing point of water. And I'm going to be really explicit here. 9.656 degrees Celsius above the freezing point of water, because now we have to relate that back to our reference point. And in Celsius, our reference point, the freezing point of water, is 0. So sometimes, people just kind of stop at this step. And if you're going into Celsius, that works. If you're using the freezing point of water, that works. But if you're using any other reference point or any other temperature unit, you can't just stop there, because this is representing a change in temperature. We need to relate that back to our reference point. So 9.656 degrees Celsius above the freezing point of water. So we have to take 0, the freezing point of water, and we are 9.656 above that freezing point. So 9.656 degrees Celsius. Now, you can look up formulas for doing Fahrenheit Celsius conversions. And if you look up those formulas, you either have to add 32 or subtract 32, and you have to multiply by either 5/9 or by 9/5. That's all in here, right? What did we do? We started by subtracting 32, but that was to give us our reference point. And then after we did that, we multiplied by 100 over 80. We'll reduce that fraction. That's 5/9, right? So we're doing the exact same process as you would with a formula, but if you just memorize a formula, you've got to make sure everything goes in the right order, in the right direction. So that's how we get from Fahrenheit to Celsius. How do we get from Fahrenheit to Kelvin? Well, we're going to start pretty much the same way. Choose a reference point. Again, let's choose the boiling point of water. Why not? 17.38 above the boiling point of water. Use the relative unit size to convert between units. 17.38 times 100 now Kelvin over 180 Fahrenheit, because again, those two are the same size. We get 9.656 Kelvin above the freezing point of water. Relate back to the reference point. We are 9.656 Kelvin above the freezing point of water, which is 273.15. So the Kelvin temperature here is 282.81 Kelvin. I rounded it to correct sig figs there. Now, when we're doing conversions between Celsius and Kelvin, because a Kelvin and degrees Celsius are exactly the same size, this ratio ends up being 1, right? It's 100 over 100, whether it's 100K over 100 degrees C or 100 degrees C over 100K. It's just 1 numerically. So when we're converting between Celsius and Kelvin, we can usually get away with just adding or subtracting 273.15 to get us into the unit we're looking for. That's a little bit about energetics and specifically temperature conversions. Work through a few examples, and it gets a little bit easier pretty quickly if you just think about the process that you're going through and not worrying about memorizing just a specific formula and when and where to apply it. We'll see you next time.